Hello there and welcome back. We can now start with the gas episode number 2. And we will learn actually today about the gas laws that derive from the kinetic molecular theory and relate the 3 state functions: pressure, temperature, and volume. So these are the topics that we'll cover today. We will study the interrelationships of the state functions: pressure, temperature, volume. You can say them in any sequence. None is more important than the other. And early on, people could do some experiments with the available tools that they had. And of course, most scientists in the old days were working at their leisure and were just interested, and it was sort of like a hobby for them, including Boyle. So we will talk about Boyle's law, which relates the 2 variables, pressure and volume, at a constant temperature. That means unchanged temperature. Then we go almost 100 years later to Charles' law, which relates volume and temperature at a constant pressure. And the problem was there wasn't a suitable thermometer as of yet, and that's why it took almost 100 years to go into this type of relationship where you can control the temperature. Then we have Gay-Lussac's law, which interrelates pressure and temperature at a constant volume. And when you combine all these 3, you get the so-called combined gas law, which allows to do any type of calculation with a given amount of variables, and the goal of the game is to find an unknown, which can be any one. So you're moving gas from one set of conditions to another set of conditions, in a sense. So you just need the 3 variables of one set of condition and have a few givens of the next set of conditions, with one being unknown. So we can do a lot of interesting calculations with these gas laws. It's a lot of fun to do, and they're very easy to do once you keep in mind these relationships. Then we'll learn also about what we call the STP conditions, and STP just strictly means standard temperature and pressure. So that's just a notion by scientists that dictated or determined 0 degrees centigrade and 1 atmosphere pressure to be what we call standard conditions. All right, let's move on. What I already talked to you about earlier in the last episode. Remember, I talked to you about the kinetic molecular theory, so that the gas particles are in constant motion, bumping into the container walls. So we have a certain pressure, we have a given volume, and whatever temperature we have. Well, what is it in this room here today? It's 24 degrees centigrade. So those are the 3 variables. Now, could you imagine now that, and I can't do that here, but let's say this is a piston, and I would move it down. Then the gas particles will have less space to move about in. So that's what actually Boyle did. He looked at the relationship between pressure and volume at a constant temperature. But before I go into that, let's look at the top of this overhead, or the slide here, or the view graph. Let's move it up a little bit. So these are actually all the laws that we will learn about in this chapter. And in today's episode, we will go up to Gay-Lussac, Boyle, Charles, and Gay-Lussac, and the so-called combined gas law. And then later on, we will learn about the ideal gas law, Avogadro's principle, and then Dalton, Graham, and van der Waals. So this is practically our program for the gas chapter. But today we will talk about Boyle's law, because that was the earliest law that was discovered, or formulated, let's rather say. Boyle was an Irish chemist and physicist. In the old days, nobody had a specific discipline. They were universal scientists, students of nature, as they often were called. And we have here in our PowerPoint slide a picture of Boyle. And he was a very nice looking gentleman, as you can see. And he worked with the air pump that Huygens developed for him. And Huygens was a close friend. And that was a benefit of Boyle, because without the air pump, he could have discovered this relationship. But we have simplified it here with a container, the little dots representing the gas particles again. And this stamp, or the piston, is one that can move up and down. So that means if we push it down, the volume gets less. But as you can already derive on your own from what you've learned, the particles, since the temperature is constant, will still have the average kinetic energy, the average molecular speeds. So the collisions are more numerous, not more intense, but they certainly are more numerous. There are more collisions per square area, or per square meters, we should rather say, or square inch if you like. So that means the pressure increases. This is already a result of your common sense. But science does not rely only on common sense. We have to numerically verify our observations. So Boyle did this, and he studied systematically various pressure-volume combinations. And it turned out that volume and pressure are inversely proportional. So we can say here in the results, volume is proportional. This is our proportional sign, 1 over P. This means inverse. Remember, we already, by common sense, determined that pressure and temperature are directly related, but volume and pressure are indirectly related, inversely proportional, at constant temperature, meaning unchanged temperature. So we can say the fixed variable is the pressure. The dependent variable is the volume. So by manipulating pressure, by willingly changing the pressure, the volume accordingly adjusts. And that means it's dependent. So the fixed variable is pressure in this case, and the dependent variable is volume, and T is our constant. So if we graph the data, then we get a slope, a curve that has a downward trend. So here we have the increase of pressure on the y-axis, and the x-axis has the increase of volume. So for the ideal gases, we have that nice curve in black. And funny enough, the green will shift a little bit when we're dealing more with real gases. And we will see later on that another law, or an extension of Boyle's law, has to account for intermolecular forces that are found in the real gases. But that we will discuss not too soon, but we will discuss it. So Boyle then, by using a constant, formulated this relationship. That means V equals constant, which is a proportionality factor actually, because we can't make an equation without having the units cancel out in a proper fashion when we want to calculate for an unknown. So V equals constant times 1 over P. Or you could say, you can put P on the other side of the equation, multiply both sides by P, and then you get the product, P times V, or the product of pressure and volume, is equal to a constant. Now this is just a constant repeatable value dimension actually. So regardless of what pressure you have, the volume always adjusts itself so that the constant is reestablished. So you always get the same value when you calculate P and V for this system at constant temperature. And that's very interesting. So that means PV equals constant, or pressure times volume is constant. I have sketched a little measuring or experimental device so that you can understand the meaning of this relationship. Let's say here's our vessel. It's sort of like a syringe in a sense, and here we have a piston that can move up and down, or stamp, or plunger. And here we have, let's say, a chlorine molecule. Chlorine is, of course, a little heavier than hydrogen, but I think because of its green color, that means in the molecular model code, green usually stands for chlorine. So they're diatomic molecules, meaning two chlorine atoms are linked together by a single chemical bond, a covalent bond in this case. And they're not sitting still like dead ducks, like in this picture, as you know. They're constantly moving around and bumping into the container wall. So they are a little bit more dilute in this representation. So the pressure is pretty weak. We have already mentioned that the temperature is about 25 degrees. 25 degrees centigrade, right? So that's the constant outside temperature, which the gas particles adapt to by virtue of their kinetic energy. So we have a constant average speed of the molecules. Now if in the volume, let's call this volume 1 and P1. If I could measure the pressure that is exerted onto the gas and calculate the volume in which the particles move about in, and I can multiply these two values or dimensions, then I will get a certain number. Now, if I push this piston down, I squeeze those or confine the gas molecules into a smaller space. That means they still, remember, they move about with the same energy, which is determined by the outside temperature. So they still have the same intensity of collisions, but remember, they have less space to move about in, so we have more collisions per area, meaning the pressure increases. But also the volume decreased, right? So we have volume 2 now and P2. Pressure is higher, but volume is smaller. If you multiply these two values, we'll get the same numerical value as we did for the earlier combination. And that's the interesting thing. If I push this down further, look, I'm squeezing the molecules into a tighter space, so they don't have enough space to move around in. The collisions with the container wall, like rabid rats in a cage. So they're moving much faster. I mean, excuse me, not faster, because remember the temperature is still the same, but they collide with the container more frequently. So therefore, the pressure is definitely increased. Not by the intensity of the collision, but by the frequency of the collisions. So we can now say we have even a smaller volume, which we might call V3, but the pressure is larger now, and we have that signified in P3. If we multiply these two values, we get the same numerical value, and of course the consistent units, which would be liters, atmospheres, because liter is usually the SI unit for volume, and atmosphere is the commonly used unit for pressure. So you see, this demonstrates how these things interrelate. So we have Boyle's law pretty well defined. Now move ahead. You see Boyle lived from 1627 to 1691. And Charles' law was established more or less in 1787, practically 100 years later. Now Charles is from France. By the way, Boyle also studied in France, so we can honor France in providing many of the scientists that worked on the early gas laws. He also worked with the law of combining volumes, which is very important, which Avogadro later picked up on again. But here we have the relationship between volume and temperature, with pressure being the constant, meaning the pressure can always balance out, so that means it can remain unchanged when you use, for instance, a U-shaped manometer. Now here we have a little picture of our Bunsen burner with temperature 1, and here we have a similar setup with a Bunsen burner with temperature 2. And let's just imagine that the second temperature is much higher than the first temperature. And here we have our container, so the gas can move about in this container and the tubing. So when we increase the temperature, the gas will move more violently, as you know, the kinetic energy increases, the velocity vectors increase, the gas wants to move out and occupy whatever space it has available. And here we have some pushy mercury atoms that can easily move out of the way and creep up into that little vacuum space here that is typical for the manometers. So even if it would be a rigid container wall, the pressure would build up. But here we have a flexible wall, so to speak, so the pressure is unchanged before and after the experiment. So we can say pressure is constant. So we have temperature 1 and V1, or volume 1, and temperature 2 and volume 2. And remember, it's practically common sense that when the pressure can give, we can sort of eliminate pressure changes. If the mercury moves out of the way, the volume will expand. So here we can say temperature and volume are directly proportional. So mathematically, I can say V is proportional to T. So we have a little proportional sign. We cannot make an equation out of this yet and use it for calculations. We need what we call a proportionality factor, which we often call a constant. So V equals a constant times the temperature. So then we can make an equation out of that. Or we can also rearrange this equation a little bit, so we have V over T equals constant. Now what was the fixed variable here? The temperature we could manipulate, so that's fixed. And then the adjustable variable, or the dependent variable, would be the volume. So the volume adjusts according to the dictations of the temperatures. The constant variable is, in this case, the pressure. So we have another interesting gas law, which we call Gay-Lussac's law. Excuse me, sorry, my mistake, Charles' law. And that means V over T equals constant. So we have the direct dependency of volume and temperature. Not like, remember, volume and pressure in Charles's law, which was inverse proportional. Here we have directly proportional relationships. Now if you graph the data that you have collected by doing these experiments, and you graph it just like we did before, only here we have temperature on the x-axis and the volume on the y-axis. And then we get a line with a slope. And the gases have different slopes depending on what gas I study. And if we extrapolate the lines backwards, then the funny thing is they will intersect the x-axis at the same point. And it happens to be at a temperature which is arbitrary for now because we can't reach it. Especially in those days, they could never reach it. Now we have better means of coming close to what we call the absolute zero. According to the kinetic molecular theory, that is the temperature at which, theoretically, no particle motions should exist anymore. Everything is at an absolute standstill. We have actually real suspended animation. Nothing moves about anymore. So that's what we call absolute zero. If you put a piece of rubber into liquid nitrogen, it loses its flexibility, and you can shatter it like a piece of chinaware or glass when you throw it on the floor. So that means particle motion is completely slowed down, and things become rigid at very low temperatures, and at absolute zero, it's a fictitious point. No motion exists anymore. So we call that 0 K, according to Kelvin, or minus 273.15 degrees centigrade. Now the line over slope, the rise over run, the angle of inclination is 1 over 273. So the expansion coefficient of gases is a constant also. Here we have the interrelationship of our Kelvin temperature scale with the centigrade or Celsius temperature scale. So in order to go from one to another, all we have to do is add 273 degrees roughly to our centigrade scale. So if I have a temperature of 24 degrees here in the studio, plus 273, and how much is that? Well, that shouldn't be difficult. 273 plus 24 is 297 K. Remember, we don't use that little degree sign. That's not allowed. So we have now covered Charles' law. And now we shall look at the third law, which is Gay-Lussac's law. Gay-Lussac. We have here an image of Gay-Lussac. He was very interested in hot air balloons, and the balloon really helped understand the gas laws, and he was very active in this research. So what can we say about Gay-Lussac's law? He was also French, about 50 years later than Charles. Here the two variables, temperature and pressure, were related at constant volume. So the fixed variable is the temperature. So that is manipulated. The pressure would adjust itself according to increase of temperature. And volume is held constant. What does that mean when we hold volume constant? Well, we do not allow any flexibility in the space for the gas to move about in, like a closed container. Remember, they always say on the bottle of aerosol cans that you shouldn't put it on the windowsill and let the sun directly shine onto it. Well, that makes sense, because we know now what a high temperature can do with the compressed gas, with the aerosol gas, or the propellant gas that we often use to put hairspray on our hair or something like that, or deodorants, etc. So the pressure builds up with the elevated temperatures. We already know that. We've learned that. So when they get more agitated in the bottle, then eventually we will reach a point where the space is violently sought out. That means the container explodes. And that's not too safe. So it is always interesting how people really set up these experiments. But here in a simplified fashion, we can learn that, well, what would you think? That pressure and temperature are also directly proportional, not inversely, so directly. So with increase of temperature, we have increase of pressure. So we have here again, pressure is proportional to temperature. If we want to make an equation out of that, we say P equals constant times the temperature. And if we want to put everything on one side, the variables on one side and the constant on the other side of the equation, then we can say P over T equals constant. Here you have now the third law, And if we combine all three, we can say, because we've learned from before, sorry, we had here a little mishap, probably by accident pushed on this button. So here we have it again. Now we can zoom into the right size of the view graph. Now we have learned that according to Boyle, V is inversely proportional to pressure. According to Charles, V is directly proportional to temperature. And Gay-Lussac, pressure is directly proportional to temperature. So we can say V times P, or the product pressure and volume, is constant. The quotient V over T is constant, and the quotient P divided by T is also constant. So why not combine them all, superimpose these laws, and then we have V times P over T equals constant. And you see this is what we call our combined gas law. And in the next view graph, we will wrap things up. And you see here PV over T equals constant. So we can also say P1, V1 over T1 will have the same value as all these three variables under a different set of conditions. So we move the gas from one set of conditions to another set of conditions, and to another set of conditions, and to another set of conditions. Regardless of what I change, the other variables will always adjust themselves according to the given laws, so that you always have a constant. So this is wonderful to work with, because then you can calculate any unknown by knowing 5 of the variables. Let's say you have given P1, V2, V1 and T1. You've given P2 and V2. Then you can calculate for T2. So you can play around with this equation any way you want. But you always need 5 givens and 1 unknown. Before we close, I did like to, let's just say, if we go from one set of conditions to another set of conditions, initial and final conditions. SDP, quickly already mentioned, 0 degree is 273 K in 1 atmosphere, which is 760 millimeter mercury or 1 atmosphere. We've covered a lot in this half hour, so I'll see you next time. Thank you for listening and watching. Bye-bye.